What would you classify as light? Although most people would think of a shining source of energy, it is much more than that. It is both a wave and particle, consisting of anything within the electromagnetic spectrum. One of the most phenomenal properties of light, however, is the speed at which it could travel, or more precisely, 300,000 kilometers per second. To show how fast that is, imagine if you saw an object travel around the Earth. If that same object went at the speed of light, it would travel about 7.5 times around in a single second. This speed is what allows instant communication all over the world, as the signals that travel are a form of light. If spacecrafts could go that fast, humanity could observe numerous solar systems, passing through various terrestrial bodies, stars, and other cosmic anomalies within just decades. However, as of today, no spacecraft has ever come even close to that speed, with the fastest space probe, the Parker Solar Probe, only reaching the speed of about 200 kilometers per second using the sun's gravity. Although fast, this would only be about 0.07% the speed of light, and would still take over 7,000 years to reach the Proxima Centauri system, the closest other solar system to us. The significance of this other solar system, however, is that it has a potential Earth-like planet called Proxima b. We know this because although we haven't seen the planet, we know that it lies in the habitable zone of its star. This could give a very good possibility for life to exist, but if it would take thousands of years for the fastest space probe to get there, let alone the other various solar systems, why haven't we gone faster? Well, it begins by understanding the concept of energy. Anything with mass requires energy to move or accelerate, with energy being anything that produces work. This can come from sources like coal, electricity, gas, and more, and the higher the speed, the higher the energy requirement. Light speed requires an infinite amount of energy, so it's an impossible goal. However, getting close to that speed is theoretically possible, although it would require an exponential amount of energy. This concept can even be seen in the equation for relativistic kinetic energy. The equation is similar to the ordinary kinetic energy equation, except there are a few more variables. These have to do with Einstein's relativity equation, E equals mc squared. But despite the extra variables, it is still the same as the ordinary equation when below 50% light speed. However, for speeds above that, the relative kinetic energy equation needs to be used. Given this knowledge though, what forms of ultra-fast space travel could we even achieve, and what would it take? To understand, we'll first talk about the kind of energy near light speed requires, using a grain of salt. Being one of the smallest things a human can see with the naked eye, it stands at about 1/3 of a millimeter and weighs approximately 6 times 10 to the negative 5 grams. This is so light that comparing the weight of a grain of salt to the weight of an apple would be like comparing the weight of an apple to that of a giant airplane. You may think that because of how light a grain of salt is, accelerating this to near light speed wouldn't take much energy. However, it is quite the opposite, as it would still require about 32 million kilojoules. To put that into perspective, that would be equivalent to the monthly electricity consumption of an average sized house. For a second, imagine spending a month without electricity just to accelerate a measly grain of salt. And it would only be that low in value under certain assumptions. One of them is that the propulsion system is 100% efficient, something that isn't really possible because not all of the energy in the system gets used for movement. This lost energy can take the form of heat, light, various chemicals, and so on. But with the type of energy requirement for near light speed being established, let's talk about something that would make light speed propulsion necessary. Known as a starchip, it is planned to weigh less than 1 gram, with its design being built off the currently lightest starchip, which is only 4 grams. Like its 4-gram predecessor though, the starchip will contain solar panels, sensors, cameras, and more, making it capable for humanity to observe terrestrial bodies in outer space. But how much energy would it take to accelerate this starchip to near light speed? Well, if it's about 1 gram, it would theoretically take about 548 billion kilojoules, which is what the state of California consumes in a month. And if this starchip were to be accelerated using the proposed method, the energy cost would double due to a 50% efficiency. However, despite the high energy cost, it would still be affordable for an agency like NASA, as its yearly budget is about 20 billion. Fortunately though, NASA plans to conduct something even better. Instead, in a project known as Breakthrough Starshot, NASA plans to launch 1,000 nanocrafts to the Proxima system. Each starship would be attached to a 4x4 meter sail just hundreds of atoms thick. A large laser array will then concentrate their power onto each nanocraft, one by one, accelerating them to 20% light speed. The high number of nanocrafts would ensure that at least some survive the journey, as even a collision with a dust particle could destroy any of the nanocrafts. But why a lower target speed? Well, it is already known that one nanocraft takes up about 2 months of energy California consumes. Now if you multiply that by 1,000, it isn't hard to see why it is pretty much impossible. And while a 20-year trip may seem like a long time, it would still be within the lifetime of most of the people managing the project, making it the best option. However, that still means that potential deal breakers exist, especially with the technology for this method not being out yet. These issues can involve things like how the nanocraft will handle the intense lasers, as well as properly reflecting them from very far distances. But what could we say about other spacecrafts? There are many kinds, each with different purposes. This can range from ones like Voyager to others like the Mars rover. The most important property to be concerned about, however, is its mass, which, as explained, could greatly affect the energy requirements. For example, there are many spacecrafts out there capable of doing things the nanocrafts couldn't, such as visiting the actual planet itself. This can include ones like the Mars rover, which would move around the planet and analyze different things. If these kinds of spacecrafts were to be launched at relativistic speeds, however, we would have to assume that they're able to visualize the small dust particles and avoid them. This can be a sensible assumption since they would be big enough to have the necessary technology. Right now, however, all spacecrafts run on fuel that either has to be carried along or is simply too weak to reach relativistic speeds. The reason fuel that has to be carried along is an issue is because of the immense weight. Normally it wouldn't be a big deal, but when it comes to relativistic speeds, the amount of weight the fuel adds up to would simply be too much. This results in even more energy needed to compensate for the extra weight, causing an endless cycle of adding energy and weight, and leading to a basically impossible energy requirement. Therefore, something like laser propulsion would have to take its place, since carrying energy would become unnecessary. But even with that problem solved, currently, the weight of these spacecrafts would still be a big concern. For example, the spacecraft UN, which landed on Saturn's moon Titan, had a dry mass of about 800 pounds. Mars rovers like Perseverance, on the other hand, have weighed more than 4 tons when accounting for all the travel gear and necessary equipment. This would mean that propelling these kinds of spacecrafts would take huge amounts of energy. For example, the amount of energy needed for UN to reach 10% light speed would be equivalent to the monthly energy consumption of France. To propel something as heavy as a 4-ton rover, the requirement would become 4 times that amount. Although that amount of energy would be possible to achieve, it likely wouldn't be done for a couple of decades. The breakthrough Starshot project, which only plans to propel 1 kilogram worth of nanocrafts, is estimated to cost $10 billion, meaning that propelling spacecrafts that weigh just hundreds of pounds would cost trillions of dollars. And this is under the assumption that the laser beams would take and expel a certain amount of space and energy, a goal that they say may not even be reached. Of course, decreasing the target speed could solve this problem, but it would also mean that a lot more waiting would occur. Already the wait time would be more than 40 years if the target is 10% light speed, so if we were to wait any longer, most of the people managing the project would likely be dead, and faster forms of space travel may exist, meaning that unless the spacecraft were to be really light, propulsion to beyond 10% light speed may not happen. But with all the progress humanity has made within the past few decades, why wouldn't we have enough energy to propel some heavy spacecrafts? Especially with the rise of shrinking technology, it could only be a matter of time before certain spacecrafts are really light and tiny. However, visiting the planet would still be an issue due to the difficulty of slowing down the spacecraft. This is because of Newton's first law, which states that an object that is in motion continues to be in motion. On Earth, there is friction, so eventually the moving object will come to a stop. However, space is basically frictionless, so once an object hits a certain speed, it stays at that speed forever. In a way, this is very good in that no additional energy is needed to maintain the speed. However, this would also create the issue of slowing down the object, meaning that unless there was a laser array or something else, the necessary fuel would have to be carried along. Different methods such as solar propulsion have also been proposed, but it has its own set of problems. Similar to breakthrough Starshot, the way it would work is that the nanocraft, with a surface area hundreds of times larger, would be deployed. The large surface area would then allow the nanocraft to absorb enough energy from the sun to go to 4.6% light speed. Upon reaching its destination, the twin stars near Proxima b would then slow it down using the same kind of energy. However, the really slow speed would make the overall travel time about 140 years, and in terms of time, that wouldn't be a feasible option. There have also been proposed methods involving the use of antimatter, where the energy from the collisions of matter and antimatter are used. This would result in 100% pure energy being released from the process, meaning that just a couple dozen pounds of this stuff can allow spacecrafts to go well beyond 20% light speed. However, antimatter is also extremely rare and inaccessible, especially since it annihilates almost instantly upon creation. Surprisingly, some have even considered faster than light travel, such as wormholes or warp drives, but those concepts are very theoretical and are pretty much considered fictional, as they involve breaking the laws of physics. Aside from the list of methods mentioned, there are numerous other methods with similar kinds of issues, meaning that as of right now, laser propulsion may be the best option available, and although this method only limits us to observing the planet from the outside, lots of information can still come out of it with different and better spacecrafts being built for it, especially when coming back to the progress of shrinking technology. For example, with cameras that have a high enough resolution, lots of details of the planet may be observed, such as its geography, weather, and maybe even different kinds of life. It is unknown if the proposed 1-gram nanocraft will be capable of this, as its camera may be too tiny, but it is expected to capture the minimum resolution of 2 megapixels. And based on the current progress of decreasing technology and increasing energy accessibility, it is certainly possible that heavy-tech spacecrafts can be launched to light-level speeds. And who knows, if an unexpected discovery occurs, extracting energy from other methods of propulsion could occur, potentially replacing laser propulsion. This could make slowing down spacecrafts possible, leading to much more exploration and available knowledge. We as a species have always done what our ancestors would have deemed impossible, like instant communication, deep-sea exploration, outer space missions, and much more. Our goal of eventually visiting other exoplanets may one day be another giant leap for mankind.